Hello everyone. Let's start solving the take-home quiz. The first question was you have to sketch the Venn diagram of silicon-based PNP BJT at thermal equilibrium, forward active mode, and saturation mode. So let's draw the Venn diagram for the thermal equilibrium mode. At first, let's define the regions. The first region is a P, then an N region, then P region, as this is a PNP transistor. So at first, let's start with the Fermi level. We know that at thermal equilibrium, the Fermi level along the structure will be at the at a level, at a certain level. So this is our Fermi level EF. And now we'll draw the conduction band and valence band. So you know that in the P region, the Fermi level should be near the valence band, right? So we will draw EV or valence band near to the Fermi level, and the conduction band should be far away from the Fermi level. So this is EV. And this is EC. So this is the characteristics of P region, where EF should be nearer to the EV. Okay. Now let's move to the N region. Here, this is the opposite. So here in the N region, the EC should be nearer to the EF. Okay. So this is EC for N region, and this is EV for the same N region. Here, this is Fermi level. So in the case of N region, EC should be nearer to the EF, and EV should be far from the EF. Okay. So and again for the P region, this is the same as the first region, where EC will be located far, and EC and EV will be closer to the EF. So this is the PNP band diagram. Now let's connect them. Connect the EC, and let's connect the EV gradually. Okay. So this is the PNP band diagram. This is the energy band diagram of a PNP BGT at thermal equilibrium. So this is number 2. We have to draw the PNP BGT energy band diagram in forward active mode. So this is the band diagram at forward active mode. So what is forward active mode? Let me clarify. Refine the regions here as well. So E, B, C. So this is emitter, this is base, and this is collector. And in the PNP BJT, it's P, and this is N. So in forward active mode, we need to connect the EB in forward bias, right? So what does here forward bias means? So the emitter should be connected to higher voltage than the base. And if that happens, this is the change in the Fermi level. This dotted line shows the Fermi levels. As you can see, if we connect it in a forward bias mode, in the EB junction, then what will happen? As you can see, the Fermi level at the base has been shifted upwards related to the emitter Fermi level. And as you can see, the difference between EC in the emitter and base region is reduced. And this is also the case for EV. So what is the final result? The final result is the barrier height. The difference between the EC in this region will be reduced. Barrier height will be reduced in the EB region. Okay. And now let's move to the BC region. Base collector region. Here, in the case of forward active mode, we need to bias this BC region in reverse bias. Okay. So the EB should be connected in forward, and the BC should be connected in reverse bias. And this is P, right? So how do we connect this BC junction to a reverse bias? We need to insert higher voltage in this N region. In the base, the base should have higher voltage than the collector. Then this will be reverse biased. And if that happens, look at the change in the Fermi levels. Okay, so as you can see that the collector Fermi level is pushed upwards, right? As you can see in the reverse bias, this happens actually. In the P region, the Fermi level will be shifted upwards in the reverse bias. And as you can see that the conduction band in the collector region is high. It's higher than the thermal equilibrium than it was in thermal equilibrium. So this is the band diagram in forward active mode. And as you can see that the barrier height between B and C, base and collector, is increased here. So compared to the thermal equilibrium, here potential barrier height between EB will be reduced, and in the BC region, the potential barrier height will be increased. So actually, why that happened? Because we know that if we insert forward bias in a PN junction, the barrier height is reduced, and if we insert reverse bias in a PN junction, the barrier height is increased. So that's it. And now let's move to the saturation mode. And in the saturation mode, as you can see, we know that in saturation mode, both emitter base and base collector, these both junctions will be forward biased. Forward, and this will also be forward biased. And this is obvious, right? Because the band diagram is obvious. As I have already mentioned that if we insert forward bias, and then the barrier height will be reduced, okay, compared to the thermal equilibrium one. And here, as you can see, in both junctions, as we have applied forward bias, the potential barrier is reduced. The difference between EC at base and collector is reduced, and also the potential barrier, the difference between EC in emitter and base is also reduced compared to the thermal equilibrium. So I think, these are, what is the difference between these two actually? The difference is here, these EB junctions are exactly the same in these two cases. Both are forward bias, right? So that's why you can see that this portion and this portion is almost the same. And what is the difference? The difference is in the BC junction, right? So in the forward active mode, the BC junction is reverse bias. That's why the potential barrier height is higher. And in the case of saturation mode, this is forward biased. That's why the potential barrier height is actually reduced. Okay, so that's how you solve that's how you sketch the band diagram of a silicon-based PNP BJT. Now let's move to the question number 2. So here in the question number 2, you have to sketch the band diagram of a silicon-based NPN BJT. Here, this is NPN BJT, just the opposite of the previous question actually. So at thermal equilibrium, as you can see that it's NPN. So NPN. We know that in the N region, EF should be nearer to the EC. That's what is shown here. And in the base, it is P region. So EF should be nearer to the EV. This is EV. Okay. And in the collector region, this is an N region. That's why the EF here, the EF is nearer to the EC, right? So this is the band diagram at thermal equilibrium. Now let's move to the band diagram at forward active mode. Let me just bring the solution here. So this is the solution. Okay. So what are the changes relative to the, what are the changes compared to the thermal equilibrium in this forward active mode? So for the NPN BJT, in the forward active mode, as I have already mentioned that this is E, and this is B, and this is C. In the forward active mode, this EB should be forward bias, right? So if we apply the forward bias, then the barrier height will be reduced, as you can see, and the Fermi level here is shifted downwards here because this is NPN transistor. So this is N, this is P, and this is N. And in the case of forward bias, we need to apply a higher voltage in this base region than the emitter region. That's how you get forward bias here. And for that, as you can see, the Fermi level is shifted downwards in the base region compared to the emitter region. And we have already mentioned that in the forward bias, the potential barrier height will be reduced. As you can see that this is the potential barrier height here is reduced in the case of forward bias of emitter base. And let's move to the base collector region, base collector junction. And we know that in the forward active mode, the base collector will be reverse biased. And in the case of reverse bias, the barrier height will be increased. Okay, and how will you apply reverse bias here in DC? So you have to apply higher voltage in the collector than base, and that will shift the Fermi level downwards in the case of collector. And as you can see, that potential barrier height is also increased here. So if you compare this with the PNP in the previous question, this is just a particle flip, I think. Okay, so this is exactly the working principle is exactly the same, just the orientation is different here. And now let's move to the saturation mode case. Let me bring the solution here. Okay. Yeah, so this is the band diagram in the saturation mode. And in the saturation mode, as we have already mentioned, that this is the emitter base is forward biased and base collector is forward biased as well. And in that case, the barrier height will be reduced. We know that if we apply forward bias in a PN junction, the barrier height will be reduced. And here in the both PN junctions, we have applied forward bias. That's why the barrier height is reduced compared to the thermal equilibrium and no bias case. Okay, So this is the saturation region. Yeah, so let's move to question number 3. So this starts true false question. So the first statement here is it is better to make the base of a BJT as long or wide as possible. It is false. We want to make the base as short as possible. Why? Because we want as many electrons as possible to reach the collector without recombining with any majority carrier holes in the base. And for this reason, the width of the base needs to be thin compared with the minority carrier diffusion line, right? So that's why we need to make the base width as small as possible. And the second thing is the second statement is the following minority carrier profile represents the saturation mode of a BJT. Actually, this is not true. This is false. Why? Uh, Actually, the minority carrier electron concentration at the edge of the BC junction is ideally zero, as you can see. Okay, so from this, what we understand that BC junction is reverse biased, but we know that in the saturation mode, both the EB and BC should be in forward biased. But here, as you can see, these are ideally zero, so we can tell that BC region is, I mean, the junction is reverse biased, and so this is not a saturation mode. Okay, now let's move to the third statement here. The following is the doping profile of a PNP BJT. So this is in the y-axis we have Nd minus Na. So here for the first region, as you can see that Nd minus Na is positive, so we can represent this like this. Nd minus Na is greater than 0, so we can write Nd is greater than Na. So Nd is the, I mean, donor, and Na is the acceptor carrier concentration. Acceptor concentration. So donor concentration is greater than acceptor concentration. That means this should be N type, right? And here Nd minus Na is negative, I mean less than 0, so we can tell that Nd is greater than Na. So here acceptor concentration is greater, so this is a P region. And similarly, this is Nd minus Na positive, so here it is N region. So this is an NP BJT, not PNP. So this is false as well. Now let's move to the true false question. No, not the true false question. The MCQ questions. Let me bring that here. Okay. So as you can see, which mode of operation of a BJT is best suited for designing amplifier circuit. This is of course forward active, because here in the forward active mode, the collector current is dependent on the base current with a relation like this, beta IB. And in other modes, IC is not dependent to IB. And here beta, the beta actually is the ratio. We're just rearranging this. It is the ratio of IC and IB, and this gives you the amplification. Now let's move to the last question here. Which of the following is true about the operation of a BJT in the active region? I mean, active or forward active region. We have told many times that for forward active mode, we know that the base and emitter should be forward biased. So this junction should be forward biased, and the base and collector junction should be reverse biased. So this is the correct answer. So thank you for listening.